Take a look at this standard representation of the real number line. In early textbooks, compactification is introduced as a simple geometric repair. We see a sequence of points escaping toward positive and negative infinity, and we resolve the problem by snapping a rigid boundary around the space, capping the ends with an artificial point at infinity. This elementary description obscures the actual mathematical work. Rather than creating a finite enclosure, compactification establishes a rigorous semantics for divergence. The structure of any boundary at infinity depends on a selected class of observables. These are the specific continuous functions, distance metrics, or degenerating geometric objects that a given theory needs to preserve. The boundary changes its shape and resolution based on our choice of observables. If we only require a single generic limit, the ends merge into a single point. If our observables distinguish between direction, the boundary splits into two distinct ends. If we care about projective geometry, the line wraps into a continuous loop. Compactification functions as a rigorous mathematical decision, identifying which escaping processes are identified as the same and which remain distinct. Consider this abstract topological space. As these two sequences escape toward the outer void, any compactification we build must first determine when these two paths merge and when they stay apart. In general topology, the Stone-Čech compactification defines observables as all continuous maps to any compact target. This vast class forces an incredibly massive boundary. Our two sequences land completely separated, preserved as distinct points on a highly fractured fractal edge. Shifting to geometric group theory, we restrict observables to asymptotic geodesics. Focusing only on large-scale distance forces, sequences that stay a bounded distance apart to become identical, the massive boundary collapses and our two paths merge into a single limit. This specific construction, developed by Mikhail Gromov, converts coarse interior geometry into manageable boundary topology. Expanding the algebra of observables refines the distinctions made at infinity. The boundary's physical size and complexity directly measures our observational resolution. In algebraic geometry, the concept of topological compactness is replaced by the requirement of properness. Properness relies on the valuative criterion, which demands that any one-parameter family of degenerating objects must eventually acquire a stable limit. Observe this smooth torus undergoing a severe degeneration. It pinches perfectly along its center until the inner cycle entirely collapses, leaving a figure-8 structure. Simply appending an abstract ideal point to represent this extreme state fails because it destroys the complex geometric data of the pinch. This graph maps the transition Deligne and Mumford used. They expanded the ontology, supplementing smooth curves with stable nodal curves. This singular object, its node recording the vanished cycle, serves as the boundary of the compactified moduli space. Modern geometry treats the boundary as a strictly classified catalog of stable degenerations designed to preserve deformation-theoretic finiteness. Divergence does not always require escaping to the edge of space. It can also mean moving infinitesimally close together, escaping into a physical collision. In a configuration space tracking distinct points, the space is non-compact anywhere two points share the same diagonal. The moment they touch, they fall out of the defined geometry. Watch these 2 points collide. Treating the impact as a single dead end deletes vital information. Zooming into the exact moment, it resolves into relative data. This boundary tree graph permanently records their relative angle and approach speed right before merging. Replacing collisions with undifferentiated points destroys data essential for perturbative field theory. Boundary objects must retain a hierarchical memory of how they were formed. In mathematical physics, the term compactification describes two fundamentally different mathematical operations. The first is Penrose conformal compactification, which was developed to analyze radiation and causal structure at asymptotic distances. By multiplying the spacetime metric by a conformal factor, the infinite grid compresses into a finite Penrose diamond. This brings null and spatial infinity to a reachable boundary, where gravitational radiation can be extracted as a set of finite measurable quantities. Compare that to Kaluza-Klein and string theory dimensional compactification, where no boundary is added to infinity. String theory assumes extra dimensions are compact internal spaces. Zooming into a macroscopic point reveals a hypercomplex Calabi-Yau manifold acting as a microscopic fiber. By wrapping these extra dimensions into compact fibers, the theory forces a discrete energy spectrum. This allows heavy modes to be integrated out while retaining light modes for an effective field theory. Both methods utilize mathematical compactness to regulate unbounded degrees of freedom, transforming them into globally constrained datasets. Because of the observable principle, we no longer seek a single correct compactification. Here, one space is surrounded by 3 boundary models. Each optimizes distinct structures: Hodge theoretic maps, canonical metrics, or polyhedral combinatorics. Wall-crossing maps translate data between these boundaries. A successful compactification provides a controlled mathematical interface, converting the behavior of divergence into structured global data. This allows us to compute with divergence, converting the act of escape into the geometry of a limit.